In order to visualize our problem, it's helpful to draw our velocity vectors. We'll start off with an absolute velocity vector here, c1, which we are told is lined up with the exit of the stator, which has a flow angle of 18 degrees. That's positive 18 degrees absolute flow angle with respect to the axial direction. So positive, of course, is counterclockwise, so we can draw in c1 like that. Downstream of that, we will have our rotor blade row, and that blade row is going to be moving to the right, oops, with a velocity of u, capital U, which we can calculate by multiplying our radius by the angular velocity. So if we put u up here as our other tangential vector, that's the velocity of our reference frame, we can then calculate the relative velocity going into our rotor, W1, just based on the vector addition, because once again, we have to have the absolute velocity is going to be equal to the sum of the relative velocity plus the velocity of the frame of reference, or if we're trying to calculate that relative velocity, it's going to be c1 minus the velocity of our reference frame. So in order to solve what's going on, we need to evaluate a few velocities. There are a couple we can calculate directly. The first is, of course, the velocity of our rotor here, which again is equal to the radius times the angular velocity. And so we can calculate that because we know that we're looking at an average radius of 8 inches for these blades. And so we will convert that to feet. So 1 foot per 12 inches. And then we're going to be multiplying by our rotational speed, which was 12,400 revolutions per minute. But of course, that's not how we express angular velocity. The true angular velocity would be radians per second. So we are going to multiply that by 2 pi radians per revolution and 1 minute per 60 seconds. So we'll get, in the end, a linear velocity for our blade row here of 866 feet per second. The other velocity that we can figure out here is actually going to be the axial velocity of the axial component of our absolute velocity. So here we know that our our compressor has to be set up to pass through 120 pounds mass per second of air, and we know the pressure and temperature of that air, so we should be able to calculate the density. And if we can use our geometry information here to get a flow area, we then we can figure out how fast the velocity has to be for that air moving through to accomplish this mass flow of 120 pounds mass per second. So first up is we want to be able to calculate our area. So the cross-sectional area of our compressor is going to be equal to, since we don't know the inner and outer radius of our span, we're just going to say it's equal to 2 pi times the radius, the average radius, we're getting the circumference here, times the height of the passage that we're dealing with. So we're going to evaluate our area here, 2 pi times 8 inches times a height of 1.15 inches, and we'll deal with this in terms of feet, so 1 foot per 12 inches squared. It's going to give us 0.401 square feet. And we can calculate our density using the ideal gas law for air. The density is equal to pressure over the ideal gas constant R, not to be confused with the radius above, and our temperature. So once again, we know that we got a pressure of 140 psi, so pounds force per inches squared, and we're going to be dividing by our ideal gas constant, 53.35, and the units here are feet, pounds force per pounds mass, degrees Rankine. and multiplying by our temperature, which was given to us as 900 degrees Rankine. And so we'll hopefully get our density here. A useful unit would be pounds mass per cubic foot. So our temperatures will cancel out, our pounds force will cancel out, and we really just have to get all of our length scale in terms of feet. So we can multiply once again by 12 inches per 1 foot squared, and that'll give us units of pounds mass per cubic foot, which would be 0.420 pounds mass per foot cubed. So once again, the mass flow rate then at that point is going to be equal to the density at 1, which is what we just calculated, times that flow area times the axial velocity, which is what we're interested in figuring out. So we can just reorganize things. Say our axial velocity is equal to the mass flow rate divided by the density times the area. And so from that, of course, we know once again mass flow 120 pounds mass per second divided by our density of 0.420 pounds mass per foot cubed. And times our flow area of 0.401 feet squared. So we're going to wind up with units here, as we would hope, of feet per second. So we'll have 712.0 feet per second as our axial velocity. So now we know the axial flow velocity, and that's at least one leg of our absolute flow vector coming in. So if that's C1, we've got our 18 degrees. We know CA1. Now if we can calculate CU1, we can also figure out our absolute velocity. So we can once again say that the magnitude of our velocity vector here, C1, since we're dealing with a right triangle, it's going to be C1A over the cosine of alpha, our absolute flow angle. So 712 feet per second over cosine of 18 degrees gives us an absolute velocity here of 749 feet per second. We can calculate the tangential component of that, taking C1 times the sine of alpha, which would be once again 749 feet per second times the sine of 18 degrees. So our tangential component is going to be 231 feet per second. So now at least our absolute flow velocity is fully defined.